The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the World Professional Automotive Community. Luke Murray from the Worldpac Training Institute is with us today. Luke has lots of experience with fuel trim, so please ask questions during the class by typing them into the questions area on your control panel. Luke will answer all your questions after the class ends. So let's get right into it. Luke, I'll hand it over to you.
All right. Good morning, good afternoon, good evening to the audience. I don't know where in the world you are, but it's breakfast for me here in California. So welcome for our latest installment of the Lunch and Learn training program. Today we are going to be discussing Euro fuel trim, also known as additive and multiplicative. And we're going to dive right into this. So full disclosure before I start, I'm a BMW specialist. That is the majority of my experience is working on BMWs, but I did work in a Euro repair shop, so I have plenty of experience on Porsche, Volkswagen, Audi. I've worked on some Mercedes, a handful of Italian supercars, and I saw a Volvo drive by my house yesterday. So I'm covered. We can get into this. So Euro fuel trim. So fuel trim in general, very useful tool for many things. Oops, let me make sure I'm on the PowerPoint here. Here we go. So useful for many things. Most commonly is the diagnostics of drivability issues or the check engine light being on, right? So customer brings a vehicle in, car's not running right. It's running rough, hesitations, misfires, or more commonly, the check engine light is on. Figure out what's wrong with it. But other, common uses of fuel trim would be the verification of repairs. That's very useful data to get in there and see that the repairs you did, whether they were fuel trim related or not, were done correctly. And fuel trim will be a pretty good indicator that the engine is doing what it's supposed to do. And then lastly, and certainly probably the least common, but I think is very helpful and useful, is during an inspection, getting an idea of the overall health of the engine. So I believe that we're all in the habit of doing, service repairs, inspections on vehicles where it's not just simply an oil change, but we look the whole car over, and we're always looking for things, to bring to the awareness of the customer, whether it's brakes, oil leaks, etc. But, I think that scanning a car, looking for check engine lights, fault codes that are in there, and bringing that to the awareness of the customer, but taking a look at fuel trim to get an idea of, things that are going on inside of the engine that may not be an issue yet, but are about to become an issue, I think would be beneficial for the customer, the consumer to be aware of. And it also, helps you out, because the last thing anybody wants, whether it's the vehicle owner, the technician, or the shop owner, is to have a car come back not long after it left the shop with a check engine light on saying, hey, ever since, you guys changed the oil, now this check engine light is on. And so if we can catch that and prevent that from happening, that's beneficial. But in order to be able to use this data for any of these reasons, we need to first understand how it works, right? If you don't understand how something works, then it's useless. That's just called guessing. And we're all great guessers. I myself, fantastic guesser, but knowledge is power. And in this case, understanding how fuel trim works, particularly on the Euro side, is going to be helpful to be able to use it. So let's take a look at fuel control. We're going to start at the start here. So here we see a fuel map. This is a 3D map. So we're showing multiple different points of data here. So running up the length of this on the vertical axis is your injection quantity. It's being displayed in milliseconds. So this is the amount of fuel that's being put into the engine, put into the combustion chamber via injector open time, right? So that's our injection quantity. Along the bottom, we have our load axis and our engine speed axis. And along the load axis, you can see that fuel is obviously added as load increases. So as load increases, the fuel quantity is also increasing. But if we look along the engine speed axis, we can see really doesn't have a massive effect on fuel. Obviously, it has an effect, but nowhere near the same as load, right? So if we look at the bottom end of our load spectrum here, and we follow along on engine speed, we can see there's really no additional fuel that's being added, and that's because no fuel is required as engine speed alone picks up. Right, all we're doing is essentially raising the idle speed at that point. And while the injectors will be opening with greater frequency, the time between intake strokes is substantially reduced. The actual amount of fuel that's required via the injector pulse width does not increase, right? And so that's an important thing to realize, because a lot of fuel maps focus heavily on engine speed, but it's not nearly as big a contributor as load is. Load is really what makes the difference on how much fuel is required. So to determine load, the engine is going to use data from sensors. On the Euro vehicles, primarily it's getting this data from an air mass meter. We have obviously different generations of vehicles we're working on, and technology constantly changes. On the left-hand side of your screen here, you'll see an older style, very, very common traditional air mass meter that's using a hot film. Those were very, very failure prone. On the right side is a more modern style. We call these cartridge style air mass meters. And that's typically what you're going to see on Euro vehicles and over the last decade. But because that earlier style air mass meter was so failure prone, just due to deterioration, contamination, it was a high failure point, and it wasn't uncommon that many technicians would be replacing these as a maintenance item. 75,000 miles, that air mass meter is probably not working the way it's supposed to anymore, and that's not a bad idea by any means. When they go really bad, they do start to throw faults, and it's going to be fuel trim faults, fuel trim limits. And because that was so common, I now see and have for a while fuel trim faults just automatically getting an air mass meter thrown on if the vehicle has any kind of mileage, and then go from there, reset the values and see what happens as a diagnostic strategy. But that is not a diagnostic strategy at all. That's a guess, right? It's a guess based on past knowledge. But in reality, these newer style sensors, they're very robust, and that largely has to do with the design. So how it functions, the hot film aspect of it is still there, right? So an air mass meter has a temperature sensor built into it. It has a film that's heated, and as air flows across it, it's going to absorb thermal energy. And the more air that flows over, the greater the mass. The air is denser. It has an ability to absorb that thermal energy faster, resulting in the temperature dropping. The air mass meter will see that drop in temperature via the temperature sensor and increase current to that film to heat it back up to the set point temperature. And then internally, that data is calculated and a signal is output either digitally or an analog signal. The newer sensor works the same way, but how it gets that air is different. And that's what really makes all the difference in its reliability and robustness. So we can see in this image here, the intake airflow comes in, but then it goes through this labyrinth passage, and there's a couple of things that are taking place in that process. One is it's functioning like an oil separator, right? So by going through this labyrinth process inside of here, oil and contaminants, dust, water droplets, whatever, can be captured and drained out before it even reaches the sensor element itself. And then the other thing to notice is the outlet, where that measured air is coming out is pointing down. And so what that does is aid in air going back across it during reverse airflow. On that earlier style sensor, that film was exposed, and it didn't matter what direction the air was going in, it always went across it. So now you're wondering, what do you mean the direction of the air, right? Air does move back pretty regularly on a vehicle. This happens anytime that the engine speed slows down. This could be just regular deceleration, but also shifting gears, right? When you shift gears, the engine speed's going to drop. Now, air that's moving into the engine has energy in it, right? It's known as velocity. That's energy stored in this moving air. But now when it gets to the engine and the combustion chamber, these pistons are moving slower, right? Maybe the throttle body just closed because you're in a deceleration event, but that incoming air, that energy that's stored in it, right? Energy can't be created, can't be destroyed. So it's now going to stack up against this slower moving component, whether it's a piston in deceleration or a throttle body that just closed. pressure wave is going to build up behind it, and it's going to bounce back out. And it's that return flow of air across these air mass meters that was resulting in this contamination and the damage, because with that air is also crankcase vapors that existed in the intake manifold due to crankcase ventilation. That's where all of that oil contamination came from. These newer style sensors, they're not going to suffer with that, because as that air pulsation bounces back out of the intake, it is going around this meter. It's not going across the sensor element. So as a result, these sensors are very reliable, very robust. They're not seeing the typical wear of an earlier style sensor. Now, the other way to determine load is with speed density calculations. We can see an algorithm up here. The good news is you don't need to know what any of that means. It doesn't matter if it's written in English or not, because the software is doing that, right? All you need to know is that it is using speed density calculation. So various inputs, primarily a MAP sensor that's measuring the absolute pressure in the intake manifold, combined with the engine speed, throttle angle, and other inputs. The engine management system and the software is able to calculate what the load is on that engine, and then determine the appropriate amount of fuel to deliver. Now, the other thing that has a large contributing factor on how much fuel is injected into the engine, besides load, is temperature. Engine temperature correction has a massive effect on fuel delivery during the warm-up stage and during cold start cranking. We can see in this sample chart here just how much additional fuel is added when the engine is warming up. So this is the engine is already running. This is not cranking. The engine is running, it's at idle, and because the engine is warming up, it needs more fuel. The reason for this is cold air does not atomize fuel as well. So when the engine is cold, the air inside of the combustion chamber is cold, the air inside of the intake manifold is cold, and as a result, that cold air is not going to be able to hold atomized fuel as well. And because it's atomized fuel that we really ignite, it's important to add more fuel in order to ensure that there's an appropriate amount of fuel to actually burn inside of the engine. The other contributing factor is that cold air is dense air, and that means there's more oxygen molecules packed into the same volume. And since air-fuel ratio is really concerned about an oxygen-fuel ratio, we need to ensure that there's additional fuel to make up for those additional oxygen molecules. But look how much fuel is added during this warm-up phase. So at 20 degrees Celsius, we're adding 22% more fuel during this warm-up cycle. That is a tremendous amount of additional fuel. In fact, there is so much deviation in the amount of fuel that's necessary based on engine temperature that manufacturers have started to take advantage of that fact and actively control the temperature of the vehicle, not only to warm it up faster, but to also be able to increase the temperature intentionally. So run that engine extra hot when it's in, an eco mode. So the hotter you make the engine, you can actually then start to reduce the amount of fuel that's used. You're thinning out the air and saving fuel. And so if this vehicle is in an incredibly low load state, like cruising down the freeway, the engine management system can intentionally overheat the engine to reduce fuel consumption. So that's done with things like variable flow or variable displacement water pumps. You have electric water pumps, so the engine management system can control the flow using either of these technologies independent of engine speed, or manufacturers are also using these very complicated spool valve style units to replace a conventional thermostat. And so having full control over that engine temperature, both to intentionally get it colder for performance gains or intentionally get it hotter for fuel savings. During cold start cranking, there is even more fuel added. So these are at engine speeds, below 400 RPM. So during that initial cranking phase, just to get that engine to do its initial fire. Look at how much additional fuel we could be experiencing in this situation, right? So in this case, we're looking at engine temperature and injector pulse width or open time. So a warm engine, in that, 70 to 80 degrees Celsius, we can see on this map is using 3 milliseconds of injector open time. And that's a pretty normal injector open time, hot idle, when the engine is running. Typically on a European manufactured vehicle, you're going to see about 2.5 milliseconds of injector open time, plus or minus, give or take. So this 3 milliseconds of open time during cranking is pretty standard on a warm engine. That's not that much additional fuel during cranking. But look at when it's colder, right? At 20 degrees Celsius, we're talking about 15 milliseconds of injector open time. That's 5 times more fuel than we would be seeing at hot idle, right? 5 times more fuel. That's 500%, right? Fuel increase during cranking. That is a tremendous amount of additional fuel that's necessary during this low engine speed in order to ensure that that engine is able to fire initially and start, right? And so temperature is very key, and it is very, very important, right? And it's something that I think has gone largely ignored. If I go back a couple slides here, if we look at these 2 temperature sensor examples on this screen, the one on the left is a temperature sensor that's been in use for decades, right? It's threaded right into the cylinder head. All manufacturers use, probably this exact same component, if not something incredibly similar. And those temperature sensors largely were reliable, right? Hardly ever replaced them, hardly ever saw any issues with them. But modern engines now have started to use, different components. And on the right, we see a thermostat module, right? This one I think is specifically off a Mini, but we see similar components on European vehicles where the thermostat assemblies in this large plastic unit that's also got valves and other things incorporated into it. And right on the top there is the engine temperature sensor. And that engine temperature sensor is available separately, but to aid on the time in doing repairs, it comes with a new thermostat module. And these thermostats are being manufactured by all kinds of different companies at varying degrees of quality. And with those temperature sensors coming with it in there, getting a low quality temperature sensor is not uncommon. It's not unheard of and can result in problems. And those will exhibit themselves as fuel delivery issues, so depending on how bad the temperature sensor is, it could just be a fuel trim related issue. The engine is running a little too lean or a little too rich and fuel trim is taking care of it. Or we may see it to the point where the temperature is so far off, the engine won't even start. You have a crank no start situation or an incredibly rough running motor during the warm up phase. So temperature is a huge contributing factor to the amount of fuel that's added. I want to make sure that we remember that and that we're aware of it. So now all of this data is looked at: temperature, load. It's all calculated inside of the engine control module, and then applying that to the fuel map, the appropriate amount of fuel is determined. It's delivered to the combustion chamber. The combustion process happens, and then on the exhaust stroke, we have a sensor that measures those gases that are coming out of the combustion chamber. So using an oxygen sensor or a lambda sensor, air fuel ratio sensor, whatever nomenclature you want to use, that then picks up on that. And assuming everything was right, the data was right, the engine is healthy and functioning mechanically the way it's supposed to, that fuel should be delivered at an appropriate ratio. And it is confirmed by the engine management system by looking at this sensor. But that's usually not the case, right? These engines are not perfect. And so we have trimming taking place. And so by looking at that data from that oxygen sensor, the engine management system can determine if it's running the appropriate amount of air fuel ratio. But if not, it can either add or subtract a little bit of fuel, and that is known as fuel trim, right? So this trimming, adding or subtracting a little bit amount of fuel based on feedback from this sensor, is fuel trim, right? And so then fuel trim, of course, can be divided up into short-term and long-term. So live in the moment adjustments are short-term, right? So every single exhaust stroke that's happening, that data is coming in, the engine management system is making slight adjustments, rich or lean, to try and get it into that perfect ratio that's ideal for the health of the catalytic converter. But if it's trending one way or the other, it's hanging lean, it's hanging rich consistently, the engine management system is going to say, wow, this isn't just a momentary problem, this is a permanent or long-term problem. And it will shift that fuel trim into long-term, where that correction is going to be applied always, regardless of what the engine running state is, regardless of the temperature, regardless of the load or the engine speed. It's always going to add or subtract this specific amount of fuel, try and get ourselves back down as close as possible to zero trim, and then let short term make those micro adjustments from there on out, right? So that's long-term, short-term fuel trim. Long-term fuel trim is stored when the engine shuts down. It's saved inside of the computer. It's immediately applied on next startup. You can see that data PID in a scan tool. But we're here to talk about additive and multiplicative. We're talking about Euro fuel trim. So how does Euro fuel trim, how does additive and multiplicative, what the European manufacturers are doing, compare to long-term and short-term fuel trim? Well, it works the same way. It's the same concept, right? We have long-term, short-term fuel trim taking place. The only difference is that the Euro manufacturers break their long-term fuel trim up into two separate categories. So additive and multiplicative are both long-term fuel trim, right? They're both long-term fuel trim. So this is the first misconception that you may have realized. It's incredible how often I will hear from technicians this belief that additive is short-term fuel trim and multiplicative is long-term fuel trim. That is not true. They are both long-term fuel trim. So does that mean that European manufacturers don't have short-term fuel trim? Of course not. They definitely have short-term fuel trim. It exists. That PID is available in your scan tool to see it. It just won't be labeled as short-term fuel trim because they just simply don't use that nomenclature. And what it will be labeled at is totally dependent on the scan tool itself, the manufacturer, and even just the year and engine that's being used. But common phrases are oxygen sensing, very common phrase that you'll see. Another one is lambda. I've seen one called oxygen sensor integrator. But these are all nomenclature that's being used to describe short-term fuel trim. That's live fuel trim taking place. And almost always it's going to be displayed as a lambda figure. So in lambda, 1 is perfect. We're not adding, we're not subtracting. But if we need to add fuel, that number goes up. So we will see 1.1. If we see fuel needing to be subtracted, we'll see that number go down. And so ideally is 1, but you'll see that number exist. Some scan tools will do the calculation inside and display that number as a percentage. So you may see it displayed as a percentage, but short term is still taking place. It is still in there. The primary difference here with additive and multiplicative is how the engine management system uses long-term fuel trim, right? And that's done by breaking it up into two categories, right? So additive is a long-term fuel correction for the idle range of the engine, and multiplicative is a long-term correction for the part load range of the engine. So why do the European manufacturers do this as opposed to long-term, short-term fuel trim, which we see in so many other manufacturers, domestic and Asian? It has nothing to do with them choosing to not do it that way and wanted to do it their own way, but rather that's just how they've done it. European manufacturers have been using oxygen sensor, feedback control, and fuel injectors and for a long time, right? And so in the late 80s, early 90s, manufacturers said, hey, you know what, we should store this data, right? Our computers are getting more powerful, there's more memory on board. We should store this data so that we're not always having to make these adjustments. And when we see these trends, why not start it off right away as soon as the engine starts? And so the idea of fuel trim was developed, and most manufacturers were buying their components from Bosch, and that was the way Bosch did it. Bosch, said, hey, this is how we should break this up and do it. So additive is long-term correction for the idle range. Multiplicative is long-term correction for the part load range. Now, this is a chart that you may have seen when studying additive and multiplicative fuel trim in the past, where it shows this idle range and this part load range sitting here. Okay, but what about all these other areas, right? What about the fuel trim that takes place when we're outside of these two operating modes? So let's first understand what the difference between idle and load is. Idle has nothing to do with engine speed, right? That is idle speed. Idle itself just simply means no load, right? Now, we can't have zero load, right? Load is always going to exist in the engine. But idle simply means that we don't have any additional load. There's no additional requirements to try and move that car, right? So the typical loads that we're going to see at idle are just always there. It's the mechanical load on an engine. So internally, just the fact that an oil pump is pumping oil, the fact that pistons are moving up and down, there's bearings, there's moving components inside of there, and that all results in friction. That's load, right? The belt is driving components on the vehicle, whether it's an alternator or a power steering pump or an AC compressor, right? These are all things that are being driven by the belt. That's additional load on the engine. That's always there. It's always going to be there. Manufacturers are doing things like moving to more electrical components and less belt-driven components to try and reduce that load, going to much thinner oil to reduce the load on the oil pump, and even variable displacement oil pumps to try and reduce that load overall. But then there's also a load that's known as pumping losses, right? Pumping losses is described as the energy it takes to move air in a vehicle. And obviously there's the intake and the exhaust side of that equation, and things like clogged air filters or clogged catalytic converters are going to add additional pumping losses to an engine because of the effort it takes to breathe through those clogged components. So manufacturers will do things like high flow exhaust systems and high flow intake systems, and porting the engines appropriately, bigger valves. All of this is done in an effort to reduce those pumping losses. Even things like variable valve lift are all done to reduce pumping losses. But there's another area in the engine that's oftentimes overlooked, and that's in the crankcase, right? The crankcase still has air in it, and that air needs to be moved around. When a piston is coming down on its intake stroke, when it's coming down on its power stroke, there's air on the backside of that piston that's being displaced and needs to be moved throughout the crankcase, right? It's going to follow a piston that's moving up on its compression stroke or exhaust stroke, right? But that's also pumping loss. That engine is using energy to move that air around in the crankcase. And this is a big reason why manufacturers are using pressure differential in the crankcase, so what we call crankcase vacuum. So using valves to regulate that, they reduce the pressure in the crankcase, which makes the air thinner. And there's less air molecules in there. There's less resistance and friction in that air, and that reduces pumping losses on the crankcase. So these are all normal loads that exist. And as long as those are the only loads that are taking place on the engine, we would consider this an idle state, right? Now, the speed the engine happens to be turning is just idle speed, right? But we can idle that engine at any speed we want, right? If that engine is at 6,000 RPM, right, but there's no additional loads on the engine, it's just sitting there revved up, then that is still an idle state. There's no additional load. But that is not common, and it doesn't make any sense. No manufacturer wants their engine to idle that high. And on the flip side, we can have load, we can have very high load at very low engine speeds, right? That's known as lugging. We should be downshifting at this point, okay? So those operating states exist, but the engine is not in those modes very regularly, right? And so as a result, this area in the red, that would be your high load, low engine speed, or high engine speed idle state, or in the case of our upper right-hand corner here, that's wide open throttle, high load, high engine speed, going up a hill. These are modes that are not being operated in for any long periods of time, and as a result, fuel trim is not really going to be applied to them in the long-term state, right? Short-term fuel trim can take care of any corrections that are necessary in those modes, because we don't care if something is trending in these areas that are not seeing regular operation. So the areas that we see highlighted in the gray and white stripes here, those are the areas that the engine is paying attention to, right? So if it sees fuel trim, a fuel correction trending rich or lean in these areas that are labeled part load or idle, that's when those trends are going to move into long term. And the engine's going to say, we stay in these modes for greater periods of time. These are the two most common states the engine is in. And so if any necessary fuel trim is trending in these areas, it's going to be added to long term to ensure that it's always being taken care of. Now, here's something that's crazy though, is what about these red areas? If we have long-term fuel trim that's being applied at idle, long-term fuel trim that's being applied at part load, our additive and our multiplicative, what happens when we are operating outside of those zones and there is fuel trim, right? When we get out of idle, is that fuel trim no longer applied? We have to rely on short term. That would result in hiccups and hesitations constantly happening as the engine transfers in and out. And that's an interesting idea. Long-term fuel trim, we just apply always when the engine is running. But when we break up long-term into these two categories, what happens during the transition between these two categories? Is there any noticeable hesitation if our fuel trims have really large numbers in them? We'll get to that. It's pretty exciting. So let's make sure that we understand these two different modes and how the engine management system treats fuel trim and then how it's displayed. So additive fuel trim, right? This is our idle range fuel trim. You may also see it being referred to as idle fuel trim or TRA, or in the case of Porsche, RCAT fuel trim. These are just different nomenclatures that manufacturers use. They're all additive fuel trim. They all function the same way. But that's your idle range area of fuel adjustment. These adjustments are made by adding or subtracting a specific amount of fuel to the base value. It's measured in milliseconds of injector open time or milligrams per stroke, and it is sometimes displayed as a percentage, although not very often. The percentage is certainly not how it's being worked in the engine management system. That's just how the scan tool is displaying it to, help it make sense to a technician. So you'll see that in a lot of third-party enhanced level scan tools, it being displayed as a percentage. But how it's functioning internally is by adding or subtracting a set amount of injector open time to the base value, right? So we saw that map at the beginning of the class where the engine looks at load conditions, etc. So in the case of idle, hot idle, the engine's up at operating temperature. We're typically looking at 2.5 milliseconds of injector open time in this idle phase. And then the engine management system will add a little bit to that or subtract a little bit of that. And so as a result, it's going to be displayed as a set injector time. So you might see additive being displayed as 0.25 milliseconds. So it's going to take that base open time of 2.5 milliseconds, and it's going to add 0.25 milliseconds onto it. So we now have a total injector open time of 2.75 milliseconds. Now you may see that number being displayed and labeled as milligrams per stroke. The first time I saw this, I'm like, oh my goodness, things just changed big time. What does that mean? Milligrams per stroke? Well, the stroke is the intake stroke when fuel is being sucked in. And so milligrams, that's the amount of fuel that's being added or subtracted to our base value. How do I even comprehend that, right? How much, I got to know how much fuel weighs, how much fuel is a milligram of fuel. And then how does that correlate to the amount of fuel that's normally in there? I spent all this time knowing that 2.5 milliseconds is my base hot idle open time. How many milligrams of fuel are being injected in 2.5 milliseconds at 3.5 bar or 5 bar, whatever it is? I don't know. This is crazy talk. Well, the good news is, as a general rule of thumb, it's almost identical to milliseconds, right? So an engine manufacturer, particularly the European manufacturers, have realized that 2.5 milliseconds is a really good period of time to inject fuel at an idle state, right? That's enough time to allow the fuel to atomize and get in there and be used. So depending on the engine displacement, if that cylinder has more air, obviously it needs more fuel. The manufacturers are going to use different fuel pressure set points or different flow rates on their injectors to ensure that the appropriate amount of fuel is injected in roughly 2.5 milliseconds. That is just an ideal hot idle injector open time for everything to work efficiently. And so as a result, what I've come to realize is that it is 1 milligram per millisecond, 1 milligram of fuel per millisecond that's injected, assuming that the engine manufacturer has dialed it in, which is typically what we see on the European manufacturers. So if you're seeing 0.25 milligrams per stroke of fuel correction, that is the equivalent of 0.25 milliseconds. So just pretend that it doesn't even say milligrams per stroke and it's milliseconds, and that is a solid rule of thumb that you can go by for diagnostics. Is it 100% accurate? No, but it's close enough for diagnostic purposes. Now, if you're building some custom tuning software because you've done modifications to an engine and you've changed the compression ratio and put new pistons in there and all kinds of stuff, and you're tuning it and you're trying to figure out what your milligrams per stroke is, well, you're going to want to talk to smarter people that know how to do that specific math. I'm not that person. But I can tell you right now, on a stock motor, European manufacturer, milligram per stroke is the equivalent of a millisecond. Now, multiplicative fuel trim, right? This is also known as our part load fuel trim. You may see that being labeled in a scan tool or in technical literature as FRA or Frau. I presume that this is German for a word that means something that's totally unrelated, but it's what it translates to. So you may see that being referred to as FRA, Frau, part load, or multiplicative. Multiplicative is a pretty common term, though, that you will see being used there. These adjustments are made by multiplying, hence the name, a specific amount to the base value. And this will be displayed either as a multiplier or a percentage. When it's displayed as a percentage, it's pretty straightforward. We can wrap our head around that. We know that 10% means 10%, right? But when it's being displayed as a multiplier, I think this is where sometimes it trips people up, right? And so a multiplier value is the number we're going to multiply that base value by to get our new injector open time. Okay, so zero correction would display as 1.00 because 1 times anything equals itself. So we have an injector open time of 10 milliseconds based on these load conditions, and we have a multiplicative value of 1 times those 10 milliseconds is still 10 milliseconds, right? But if we need to add or subtract fuel, in the example here, we need to subtract 10%, so negative 10% fuel correction has a multiplier value of 0.90, right? Because if we take that 10 milliseconds and we multiply it by 0.90, we will get 9 milliseconds, right? That's a 10% reduction. On the flip side, if we need to add fuel, we will see a multiplier that results in that. So positive 10% is the same as 1.10, right? This is simple, easy math to look at because of the fact that it's a multiplier, and converting a multiplier to percentage is just moving the decimal point, right? Or doing the math. All right, so in the case of positive, if we saw 1.23, that's the same as 23%. You know, if we saw negative 0.78, that's minus 12%. Okay, so that is how our multiplier value is being displayed. And it's important to understand because, you know, I've seen individuals get caught up on this and just assume that they're looking at a percentage value because that's what they're used to. And if you go into your scan tool and you see, oh, wow, I've got, you know, multiplicative fuel value of 1.15, and in your brain, you're thinking that's percentage, 1.15%, that's not much, right? That's pretty solid. I'm happy with that. But in reality, it's 15%. It's substantially higher. So understanding that that's what a multiplier is, and that's how multiplicative values are typically going to be displayed in a scan tool. If you don't see that percentage sign, it's displaying a multiplicative value. Okay, so remember earlier I talked about that chart and what happens as we transition from one range to the next. Well, there's no transitioning from one range to the next because with additive and multiplicative fuel trim, both corrections are active in all ranges, right? So that means if we have a additive fuel correction, that additive fuel correction of plus or minus whatever milliseconds, that is being applied in all instances. Right? So it doesn't matter if that engine is at high load or low load or idle, it is always adding or subtracting that set amount of fuel. It's long-term fuel trim and it is applied under all driving conditions. The same is true of multiplicative, right? So a multiplicative value is being applied at all conditions. If you have multiplicative fuel trim, that is also being applied at idle. So a multiplicative value of 1.10 or 10% means it's going to add 10% at idle also, okay? So these are both playing together at the same time, and that's why there's no transition from one mode to the other that's going to result in any kind of hiccuping or hesitation as it moves from one type of fuel trim to another. They're both being applied. The difference is whether it chooses to apply fuel trim to one or the other. Right? So remember, fuel trim is happening because of a trend. Right? The engine management system is looking at values on short-term fuel trim, right? And if it sees it trending one way or the other consistently, it's going to apply that to long-term fuel trim. The difference is, where is that trend taking place? Right? Is that trend taking place at the idle state? So in the idle range, the idle zone, this is where we see fuel trim trending, right? Consistently needing to add fuel that is going to then be moved into additive long-term fuel trim, as opposed to a fuel trim trend, right? A richer lean condition that's consistently happening in the load area, that's going to be applied to multiplicative. And the reason is just how well it works, right? At idle, we saw in that map that at idle, we have a pretty constant fuel delivery. And so by making really subtle corrections, by adding a set amount of injector open time, the engine management system can really fine tune the idle, as opposed to part load. You know, that map was all over the place, right? A little bit more load means a lot more fuel. And so having a percentage factor or a multiplier factor for part load, it makes sense there. And then again, if the fuel is trending richer lean outside of these two correction zones, short-term fuel trim is going to take care of it, right? But if there's any long-term fuel trim already in effect, it's going to affect all of it, all ranges always, right? These two zones just determine when something shifts from short-term to long-term and whether it goes to additive or multiplicative, okay? So that is the core of additive and multiplicative fuel trim. They are both in effect at all times, right? And the reason why it's okay to have this idle fuel trim correction taking place under all ranges is because it doesn't have as much of an effect, right? If we're adding, 0.2 milliseconds of fuel correction as additive in our idle range, just to make sure we have that nice smooth idle, adding that 0.2 milliseconds to the engine when it's under load and its base injector open time is 16 milliseconds, that little 0.2, no big deal, right? Short term can easily make up for those little tiny subtle adjustments, okay? Multiplicative fuel trim being applied at the idle range, right? If it's not necessary, then your additive correction will add on to it and make an adjustment. So they're constantly working together. And when we look at some samples here of how you would use this fuel trim from a diagnostic standpoint, I think that'll start to make sense. So now that we understand additive and multiplicative, how the engine management system uses them, and that they're in use together at the same time, right? It's just the measuring process of when something moves from short-term to long-term, where it puts it, what two types of long-term fuel trim it puts it into. So now we're going to look at some samples here as we go through some diagnostic techniques. So we have a vehicle, it's running rough, customers complaining, check engine light is on, we've got some fuel trim fault codes taking place. You scan the car and you take a look at this data. So here we have bank 1 and bank 2, right? Engines have banks, right? That's really based on the amount of oxygen sensors that are on the vehicle. So European manufacturers, you have a 6-cylinder engine, you'll typically have 3 of those cylinders on one bank, 3 of the cylinders on another bank. A V8 engine, you've got, the 2 sides of the engine are 2 separate banks. I've seen up to 4 banks, V12 motor using, 2 banks on each side of the V, so 3 cylinders per bank. So, I think we can all wrap our head around that and understand the bank concept. But with fuel trim is bank dependent. So here in this example, we see our multiplicative fuel trim at 1.01 on bank 1 and 0.99 on bank 2. So that's the equivalent of bank 1 adding 1% of fuel and bank 2 subtracting 1% of fuel. That's pretty close, right? That's good. I'm happy with those numbers. Right, but on our additive correction, we do definitely see a problem here, right? Here we have fuel being added, right? There's no minus sign there, so this is fuel being added. On bank 1, 0.92 milliseconds, and on bank 2, 1.02 milliseconds. So both banks are adding fuel pretty close to the same amount of fuel is being added to both banks. So this is a systemic issue. This is the whole engine that's happening too. But this is an issue that is primarily in the idle range, right? It's being added in that idle range. Multiplicative numbers are pretty good. So once this engine is outside of idle, there's not a whole lot of fuel correction taking place. The engine is pretty healthy. So we have an idle problem here. This is an engine that's running lean at idle, right? This is a classic example of an unmetered air leak. So whether that's a vacuum leak or a torn intake boot, right? This is a situation where the engine is running lean at idle and a fuel correction needs to take place and it's being stored in there. So this is where we see the beauty of additive and multiplicative, and why the Europeans manufacturers decided to go down this road. With traditional long-term, short-term fuel trim, a vacuum leak is going to see fuel correction. Fuel is going to be added to it, and if the engine is sitting there idling for long periods of time, especially if they're a commuter in Southern California, that might be sitting on the freeway in an idle state for an hour and a half every morning, right? And so now long-term fuel trim is going to be adding all of this fuel that it sees due to this lean condition at idle. But then once you get off the road and start driving, now we're rich, right? Because it doesn't need that fuel under load. So now the traffic clears up and you're cruising at a nice steady load down that freeway, and the engine is running rich. And so now short-term fuel trim is subtracting fuel, eventually long-term kicks in, our numbers settle back down to zero. But then once you come to a stop sign, you've got this hesitation on this engine again. It starts running and idling rough. So the European manufacturers realize that vehicles do spend long periods of time in these two common driving states, and to ensure that the appropriate amount of fuel correction is always happening for a very consistent running healthy engine. That's why they did that. So knowing that and seeing this data, we can look at it, right? And we have a good idea from looking at this data that this is an idle problem. This is a lean running condition at idle. And we can see that without even having to run the engine. This is long-term fuel trim data. This is stored in the scan tool, right? Diagnostics is all about, testing things to verify that they work until we find something that doesn't work, right? And so that's the whole process of diagnostics. But before we start to do any testing, I like to gather as much information as possible, gather all of that data, look at it, and then develop an appropriate test plan. Because there's nothing worse than doing a test that's unnecessary, right? In the condition of this engine here, I know that I have a fuel trim problem. That was the check engine light that came on, right? But then when I look at the data, I can rule out so many things, right? Because my multiplicative values are good, right? I know that I don't have a systemic fuel delivery problem, right? This is not a bad fuel pump. This is not a pressure or a flow problem. This isn't an air mass meter problem, right? This is a lean condition at idle, and I will choose the appropriate tests to then find it, right? Get the smoke machine out, start looking for those vacuum leaks, do a visual inspection for torn intake boots, and don't overlook the crankcase, right? Because the crankcase is part of this breathing system, and a crankcase leak is a false air leak, right? And so a leaking rear main seal can be causing these exact numbers right here, because that air is getting sucked into the crankcase, and we have a crankcase ventilation system that's trying to maintain a set pressure differential through the crankcase vent valve. But if air is being sucked in through a rear main seal or any leaking gasket on that crankcase, that's air that's getting sucked into the engine. And you would see similar results. So understanding the data and determining an appropriate test plan is so valuable. So let's take a look at another sample here. Right here we have our multiplicative values, again, pretty similar, 1.01 on bank 1, 1.02 on bank 2, right? So that's adding 1% and 2% respectively. I'm okay with that. That's all right. Okay, but again, on our additive side, that's where we see problems. So this is an issue that is primarily being affected at idle, right? But it's only on one bank, right? Bank 1, it's adding 0.12 milliseconds. That's not a whole lot. I'm okay with that. That's certainly not where our fault or our check engine light is. The problem is on bank 2, 1.13 milliseconds of injector open time is being added there, right? That's a lot, right? 1.13 milliseconds. Right, if we consider our base injector open time of 2.5, that's almost 50% of additional fuel correction in the idle range, but only on one bank, right? So this is not a systemic problem. This is a bank-specific problem, and so as a result, again, this is not a fuel-related issue with regards to the system. So it's not a fuel pump, it's not a fuel delivery issue, it's not pressure, it's not flow. And because it's just one bank, it's not an unmetered air problem either, right? Because an unmetered air problem will result in something systemic that's affecting the whole engine. This is something that is bank specific. But at the same time, it's running very lean on one bank, but only at idle, right? Because we can see our multiplicative values are okay, all right? So this is a correction, again, that's being applied across the whole operating range, okay? This right here is a sticking fuel injector. Right, that is what we're looking at here, right? So a fuel injector, the way it functions, there's a spring that's keeping it closed and sealed. but then a magnetic field is generated inside of it to overcome that spring pressure. And that is known. The amount of energy, the size and strength of that magnetic field to overcome the spring pressure is known by the engine manufacturers. It's built into the software. So an appropriate amount of electrical injector open time, the actual TI signal, right, that pulse width, is known, and some of that time is being used to physically open the injector to build up that magnetic field until it opens. And then the rest of the time is the physical injector open time. That's the period that fuel is being injected. But if we have a sticking injector, right, whether it's carbon buildup or just fuel varnishing on the pintle that's resulting in additional resistance, now that magnetic field has to be stronger. And so where the injector should have physically opened, it's not opened yet because it's sticking. So the magnetic field is continuing to build until it has that additional strength to overcome the spring and this mechanical resistance. And so our physical injector open time is reduced. And that's what's happening here. The engine management system is adding an additional 1.13 milliseconds of injector open time to overcome that resistance, right? So now the physical injector open time is what it's supposed to be. And because that sticking injector is going to be sticking at all engine conditions, you know, it doesn't matter if the engine is 7,000 RPM or 700 RPM, it doesn't matter if it has 10% load or 90% load, that injector is always going to be sticking. And so that added correction of 1.13 milliseconds makes up for the sticking injector, right? And then we're good. That's all it needs. It doesn't need any additional multiplicative correction under load because it was just a sticking injector. Now this is one bank, right? And how many cylinders on this bank? Could be 2, 3, 4 cylinders on this bank. It's only one of the injectors that's actually sticking. I mean, I know it could be more than one, but it's probably just one. And so the rest of the bank is making up for it. So again, this is just an average. This is an average of that bank, and that's what it takes to make sure that the whole exhaust stream is average, you know, lambda 1, that stoichiometric air-fuel ratio, right? But so you can see how understanding the data, right, we can start to gather an idea of what the problem could be on this engine. Now we look at this example here. We have additive fuel trim values, 0.12 milliseconds, 0.13 milliseconds. Those are okay. Those are totally reasonable numbers, you know, for an engine with any kind of miles on it. But our multiplicative values are high, right? We have 1.21 multiplier on bank 1 and a 1.20 multiplier on bank 2, right? So that's 21% and 20% respectively that's being applied across all ranges, right? And so this now is a systemic problem. This is classic fuel delivery, right? Clogged fuel injector, or clogged fuel filter, a low outputting fuel pump, right? That could be a result of a power supply to the fuel pump and it's just not turning as fast. It could be the pump is worn down, right? But this is a fuel delivery issue, right? In the case of modern engines that are using fuel pressure sensors and variable speed fuel pumps, this could be a case of a bad fuel pressure sensor, right? So the engine management system thinks it's putting the appropriate amount of fuel in there, but it's not because that sensor is reporting false data back, right? But that multiplicative correction factor, right, that additional 21 and 20% of fuel is appropriate at the idle range, it's appropriate at the high load range, it is being taken care of there. This is a fuel delivery problem that we are observing. Now let's take a look at this one, right? So here we have, again, 20% of additional fuel that's being necessary across the part load range during most of this engine operation. However, at idle, when that additional 20 and 21% is being added, it is running too rich. So at idle, it's now too rich, so fuel is being subtracted. We can see a reduction of 0.92 milliseconds on bank 1, 1.03 milliseconds, pretty even numbers there, right? But this is fuel being subtracted. So by adding this 20 and 21% to the fuel map overall, because remember, multiplicative also kicks in the idle state also, that is resulting in it being too rich at idle, so fuel needs to be subtracted, okay? So this is a situation where the engine is running lean under most operating conditions, certainly during part load, but not at idle, right? And in fact, that additional fuel correction is resulting in it being too rich. This right here is a classic example of a bad air mass meter Okay, so those air mass meters, they get contaminated. We talked about that at the beginning of the class. Oil contamination, whatever gets on it, and that results in the air mass meter not functioning correctly and struggling to measure higher engine mass, right? At low engine speeds, low mass coming across that sensor, it's doing a good enough job of calculating the amount of air that comes into it. But once that thing starts to ramp up, that signal just falls off, right? If you were to test this air mass meter, if it's outputting an analog signal, you'd see, 0.8, 0.9 volts roughly at idle, pretty standard number that we would expect to see. But then you get that engine under load and you can barely get 3 volts out of it, right? Where it should be able to get well over 4 volts coming out at a very high load, right? And so because of that, when the engine is under load, the air mass meter is reporting an inappropriate amount of air, not enough air. Fuel correction factor takes place, but because the data is accurate at idle, it's now running too rich, and so that fuel gets subtracted out, right? So this is right here what happens with an air mass meter, and for so many years I was just taught, if you see fuel trim going in opposite directions, additives going negative, multiplicative is going positive, that's a bad air mass meter, right? I was like, okay, and I put a new air mass meter and it fixed it. But it was years before I fully understood why they go in this direction, and that is why, right? It's because additive and multiplicative are both in play always, and so that multiplicative correction factor, part load correction factor at idle is too much, and so additive kicks in and takes its place. We'll take a look at another example here, and in this case we have our additive fuel trim is negative, right? So we're subtracting 84 milliseconds, we're subtracting 0.73 milliseconds, 0.84 milliseconds. But also on the multiplicative side, we are subtracting fuel, 0.87, right? So that's minus 13%, 0.90, that's minus 10%. So this is a situation where the engine is running too rich under all driving conditions. Okay, so this is a fuel delivery problem, a systemic fuel delivery problem, where the engine is delivering too much fuel regardless of what operating state it's in. This could be a bad air mass meter. It could be a bad fuel pressure sensor. This is a systemic problem, but this is an indicator of bad data coming into the engine, right? Bad data is coming in, so it's running too rich. It's unlikely to be a mechanical problem, but it could be, don't rule it out. But this right here looks like a pretty classic, it could be the wrong component is on the car. I've seen, incorrect injectors installed on a vehicle that obviously wreak havoc. But in this case here, the engine is running rich in all conditions. Could be bad software. It could be inaccurate fuel pressure. There's a lot of things that could cause this. This is a case where we're going to go through all of our tests, right? But the one test I'm still not going to do in this condition is a smoke meter or smoke test, right? I'm not looking for vacuum leaks on this car, right? And so again, it's, I've seen it so often. Vehicle presents itself, check engine light, what's the fault code? Fuel trim limit reached, boom, smoke machine comes out right away. It's fuel trim problem, smoke machine is coming out. But look at the data, see what's happening. This could not be caused by a vacuum leak, right? This is a problem more than likely of bad data. So we are going to be looking at our sensors and comparing them to real life information. Look at what the scan tool is reporting. What is the fuel pressure sensor saying? But what is the actual fuel pressure? So we're hooking up a fuel pressure gauge and comparing that information to the information that's coming out of the scan tool, right? This is a data problem here. All right, we're getting close to the end of the hour here. And so before I take questions, I just want to take a quick look at some new technology and how that plays into effect with additive and multiplicative fuel trim. So this right here is the Bosch LSU ADV sensor, right? So the Bosch era of wideband sensors, we saw the 4.2 and then the 4.9. 4.9 is an industry standard now, but this is the latest, greatest sensor from Bosch. It's the LSU ADV, and manufacturers have begun using this. One of two of the incredible things about this sensor, one is its heat up time. This sensor is in operational readiness, so ready to go into closed loop in less than 10 seconds after cold engine startup, right? That's amazing, right? But the other thing that it's able to do is it reacts so quickly to changes in air fuel ratio that at low engine speeds, it is capable of detecting individual exhaust pulses. It can switch so rapidly that as a result, this sensor is being used by some manufacturers for cylinder-specific fuel trim correction in the additive range. It's only doing it for idle. And I've seen manufacturers do this with up to 6 cylinders. So this sensor is being installed in an inline 6-cylinder engine with just one oxygen sensor, and it is able to accurately determine individual exhaust pulses to make cylinder-specific corrections. The wild part is that data is not displayed at all. Because you can have cylinder-specific fuel trim corrections, there's no longer a limit, right? Limits are in place to ensure the safety of the engine. If you don't know what's happening and you're averaging 3 cylinders together or 4 cylinders or 6 cylinders together, and you don't know if you have a specific cylinder problem, you are only going to make so much correction before you're in the danger zone, right? You also don't know if the oxygen sensor is bad, right? Or you have an exhaust leak that's reporting incorrect data. And so we just keep leaning that engine out as a result of false data through a bad oxygen sensor or an exhaust leak. We can end up running the engine so lean that we start burning exhaust valves, right? And on the opposite side, if it's biased lean and we just keep adding fuel, we could melt a catalytic converter. So limits exist by the manufacturers to ensure the safety of the engine if fuel trim is flawed. And so that's why it's there. But in this case, because we have cylinder specific fuel trim, it can compare one cylinder to the next to rule out exhaust leaks or bad oxygen sensors. If it sees a problem with only one cylinder and not on the rest, then it can rely on the data that's coming in, right? If it's a systemic problem, it's going to apply that to multiplicative fuel trim. But if it's a cylinder specific problem, it's going to apply that to additive fuel trim. But the data is not shown, right? There's no limit. If there's no limit, there's no fault code. If there's no fault code, there's no data. Classic European strategy, limiting the amount of data that is shown to us. If there's no fault code, there's no problem. So that is taking place. And as a result, you may see on these newer vehicles when scanning for fuel trim information, you don't even see additive fuel trim, right? So if all you're getting is multiplicative fuel trim, it is probably because it has this newer style sensor in it. Additive is still taking place. It's being done at the cylinder specific level, and that information is just simply not being displayed. The engine management system will add as much fuel or subtract as much fuel as possible, as needed to correct that issue. And if it can't, it's going to result in a misfire, and that's the fault you're going to end up seeing as a misfire fault. Direct injection. Direct injection, very commonly being used, GDI, on vehicles now. How does fuel trim work in this type of engine? The same way. It works the same way. The only difference is how what it does with that fuel trim information. So it still has additive ranges. It still has multiplicative ranges for those idle and part load zones of the motor. The difference is that the injector open time on a GDI motor is way less than 2.5 milliseconds at hot idle. It's just under 1 millisecond. So that correction number will differ. Injector open time is a PID that you can see in the scan tool. So you can look at what the injector open time is and then correlate what your additive injection translates to. Is it a lot or is it a little? And then multiplicative fuel trim is going to be, adjustments are going to be made on the systemic level. So if the whole engine needs a substantial amount of fuel, 10%, 12%, whatever, added or subtracted, that is not being done with injector open time, but rather with the quantity control valve or whatever the manufacturer calls that device. But it is the solenoid on the inlet side of the high pressure fuel pump that regulates the amount of fuel coming into the system, right? Which has a secondary result in fuel pressure going up at the rail, up to potentially 200 bar in some engines. But that is how they will regulate systemic fuel trim. So instead of just using the injector open time, they will add more fuel into the system, and you'll see that correction take place in the form of an increase in fuel pressure, but the multiplicative value will still be displayed the same. Now, the caveat there is if there is a bank-specific issue, so a difference between one bank and the other, that will need to be done with injector open time, but anything that's the same on both banks will be done with the quantity control valve on the high pressure fuel pump. And then lastly, turbos. What about turbocharging, right? What effect does that have on fuel trim? it doesn't have any effect on fuel trim. It still functions the exact same way. Fuel trim works identically, regardless of whether there's a turbo on there. One of the advantages to GDI and turbo is more sensors on the car. So a lot of things that could have resulted in fuel trim issues are actually going to be caught before that case. So in the case of turbocharging, an example would be a boost leak, right? So our intake is not sealed appropriately. And so we have a boost leak. So that's air that's being measured coming into the engine, but then it leaks out before it makes it to the combustion chamber, which would result in a rich condition because additional fuel is being added, but there's no additional air to go with it. But before that even becomes a fuel correction or a fuel trim problem, the engine management system is going to recognize that boost leak through the pressure sensors on the intake manifold, and it will immediately set fault codes related to boost problems and air management problems long before fuel trim ever takes place. So when you're seeing fuel trim problems on a turbocharged direct injected engine, those systems are already being highly looked at, and any faults that take place in those systems respectively, those are going to trigger long before a fuel trim related issue happens. So from a diagnostic standpoint, et cetera, these new technologies are not making any difference to the diagnostic strategy of fuel trim. So that being said, we will open this up to questions. I realize that it is your lunch hour is over, so some of you may have to go. If you jump off, thank you for joining. If you have any questions, please feel free to email them. But at this time, anybody that's hanging out, I'm more than happy to take those questions now. Bruce, do we have any questions?
Yeah, thanks, Luke. That was really, really informative. We do have a couple of questions. The first one is from Chip. Are you for or against adaptations after performing a fuel trim repair?
Oh, that is an awesome question, Chip. Thank you for asking. I am against clearing fuel trim adaptations, regardless of whether it's after the repair or initially during the diagnostic stage, particularly initially during the diagnostic stage. I've seen far too often times, a vehicle presents itself, the European vehicle with a check engine light on, you scan it and it is just full of fault codes, right? There's so many fault codes, you're like, oh my goodness, where do I even start, right? So you clear all the fault codes, you clear your adaptation values, you go and drive it and see what comes back as like your first step of your diagnostic strategy. And that is a really, really bad idea. Particularly with regards to the cold start situation. So we saw earlier the amount of fuel that's necessary during cold start, cold cranking, warm-up phase. And if there is a fuel delivery problem, if you have a bad air mass meter or a bad temperature sensor on the vehicle, that fuel trim is being applied during cranking and during the warm-up phase. It's not waiting until that vehicle goes into closed loop. And if you clear those datas out and that fuel is necessary, you could inadvertently create a crank no start situation that didn't exist before. So vehicle comes in, it's running, it might not be running great, and check engine light is on and a whole bunch of fault codes. And then your first step in diagnosing it is making a crank no start problem. And that's a tough one to explain to a customer. It's also a really hard one to diagnose. So definitely do not delete adaptation values as your first step in figuring out what's going on with the car. And then with regards to Chip's question specifically, after a repair is completed, I do not like to delete fuel trim values. I like to see those self-correct, and that really ensures that the job was done right, because it's going to do its job and it's going to do it quickly. But thing to keep in mind here, and it's a good time to point out the difference between the generic side, OBD2, long-term, short-term fuel trim, versus the Euro side of additive and multiplicative. Obviously, long-term, short-term fuel trim still exists. If you hook up an OBD2 scan tool to a European vehicle, you will see that data. But the interesting thing is, because long-term is broken up into two separate categories on the Euro side, and in fact, in some high-end, high-performance European vehicles, they have multiple load areas. So you might see FRA1, FRA2, et cetera. Not that common, but you are adding, your additive correction and your multiplicative correction, and they're working together. And it's not until the engine shuts down and that data is stored that it updates the OBD2 side. So you could be looking at enhanced side and you could be seeing fuel trim corrections changing. But if you're only looking on the OBD2 side, they're not changing. They're just staying the same. You're like, oh my goodness, what's going on here? And then you shut the engine off, you let it go to sleep. 20 minutes later, that data is stored, and now the OBD2 PID is updated. So you go back out to that car an hour later and turn the key on, hook up your OBD2 scan tool, you look at fuel trim, you go, whoa, they're totally different. What happened? The engine wasn't even running. How could changes have taken place? And that's what's happening there. So what I like to do is taking that into consideration after a repair. I'll start the car, let it idle, and I'll let it idle for a while. Let it get up to operating temperature, and then let it continue sitting there idling for at least 7 minutes while additive correction starts to take place, right? And now we'll see an additive correction in there, or hopefully goes away. All right, but then I want to drive the car. I need to get it under load. And what you don't do is just sit there and rev the engine up to 3,500 RPM, because you are still in an idle state. Just because you're sitting there holding the engine at 3,500 RPM doesn't mean that we're not in an idle state anymore. We're still idle. So we're not going to get any multiplicative correction taking place at that higher engine speed. You need to drive it. That engine needs to be under some kind of load. So I get out on the freeway, some mild driving, 10, 15 minutes, and then your multiplicative correction will self-correct. But now it needs to also look at any additive that took place. So now when you get back to the shop, let it idle again for another 10 minutes so that because now that multiplicative correction is being applied to idle, so that additive correction might need to make a secondary adjustment to write itself out. So that's the strategy that I use. I don't like to clear adaptation values, with rare exceptions, and that's post-cat trim limits. It's not a common fault you'll see. In fact, honestly, I could say there's only one vehicle that I've ever seen it on, and I've seen it a lot, and that's the first generation Minis that were manufactured by BMW. And an exhaust leak would result in a rear Cat O2 sensor applying fuel trim. It's like fuel trim 3 correction, a Cat savings fuel trim. You can see that data on the OBD2 side. You cannot see it on the enhanced side. But if it hits a limit, it will set a fault, and you'll have this undecipherable fault code description of the front O2 sensor and the rear O2 sensor disagree with each other, and it's making these corrections, and then an adaptation limit. You look at your adaptation values and they actually look pretty good, but it's this hidden adaptation value that if you don't clear adaptation values, you will keep getting this fault come back because it's pegged. But again, it's unless I see a fault code that's specifically stating that the rear O2 sensor fuel trim is causing a problem, I'm not deleting adaptation values. No.
All right.
Thanks for asking that.
Another question from Jim. Is additive and applicative fuel trim applied even in open loop?
Yes. Yes. The answer is yes. During open loop, it will be applied always. So, but again, these vehicles are, using wideband oxygen sensors. They're at operational readiness. At LSU 4.9 is at operational readiness in less than 20 seconds, and then it's always going to be in closed loop because the range is so broad. So there's very little open loop time anyway, other than your initial warm up phase. But yes, they will be applied during open loop. There is a pre-wideband oxygen sensor era. So we go back to earlier European vehicles. If a fuel trim limit is reached, so it maxes out 25%, and it doesn't see any change. So we have a narrowband oxygen sensor, and it's pegged rich, it's pegged lean, it's not doing anything. It's so far off the spectrum, and so the engine management system continues to add fuel, and it maxes out. I'm adding 25% multiplicative. I'm adding, additional additive fuel trim, and I'm not seeing anything come from that oxygen sensor. At that point, the engine management system will actually delete all adaptation values because it now is wondering, maybe this is a bad oxygen sensor or an air leak, because after adding all of this fuel, it's not even seeing a blip in that feedback. So at that point, it will actually default to 0. And this is something you may have seen when we're talking about, European vehicles manufactured in the 90s. The vehicle presents itself. It's got fault codes for, fuel trim limit reached, rich or lean. both banks, additive and multiplicative, and then you go and look at your fuel trim data and it's zeros. It's all zeros. You go, well, what's this? That's what happened, right? That's that case. So instead of not applying it during open loop, it has that backup strategy for the older sensors.
All right, we got another question. Right. Aaron, is short term added to long term, or does it operate off base trim?
They are added together. Short term and long term are added together. Yeah, they're both working in conjunction on top of the base trim.
Okay, and Chip has
base value.
Can you have fuel trim on additive and still have multiplicative at 0?
Can you have fuel trim on the additive side and have multiplicative at 0? Is that the question?
Yes.
Yeah, absolutely. Yeah, that's your lean, that's a vacuum leak. That's an idle specific fuel correction problem that a correction is only necessary in the idle range. That fuel correction is being applied across the whole range. So you'll have a tiny bit of multiplicative fuel trim, but not much, right? It might even be out to the 1,000th of a degree, which is not even going to be displayed on scan tool. So it will show as 1 or 1.01. Absolutely. If it is an idle only problem, you will see your fuel trim taking place in the additive range, but if it's an idle only problem and it's no correction is necessary in the part load range, you could definitely see multiplicative values of 0% or 1.0.
All right, so the last question is from Linny. Is it possible to show the multiplicative fuel trim slide again? It's the slide before the multiplier values.
Yeah, absolutely. Oh, what did I do? I just ended the PowerPoint here. Let me restart it. And we will go back to this slide here. Yes.
Okay.
There you go.
All right.
I don't know if you have a question regarding that slide, or if you just want to take a photo of it or take some notes. But
all right. Well, I think we've come to the end here. So thank you, Luke, very much. And thanks everyone for being with us today. If you have any further questions about today's class, send us an email. It's wti@worldpac.com. Make sure you include the class number. This is LTT411 in the subject line. And please take a few minutes to fill out the survey. We're scheduling classes for 2024, so your comments will help us to make sure that we're providing you with the training that you really need. Any final thoughts, Luke?